When simulating multi-phase flows on fixed grids, we must update the density and viscosity fields along with the fluid velocity. This can be done in several different ways, and in this segment we'll give a brief overview of the different strategies most commonly used. In the following lectures, we will then describe one approach, front tracking, in more details. If the material properties in each fluid are constant, we do not need to keep track of where every fluid point goes, but simply know in which fluid we are. Thus, the problem is reduced to updating a marker function identifying each fluid. Although a material property such as the density can be used as a marker, here we will assume that the marker is an index function h, that is 1 in one fluid and 0 in the other, assuming that we are working with two fluids only. Once h is known, the density and viscosity and other properties can be set as a functions of h. The marker function moves with the fluid, and we can therefore, at least in principle, find where h is 1 and where h is 0 by solving a simple advection equation stating that the time derivative of h plus the dot product of the velocity with the gradient of h must be equal to 0. You may recall that the sum of those two terms is the material derivative, and the equation therefore says that h of a given material point does not change, which hopefully seems reasonable. Pushing a blob of a marker function that identifies a given region by a given velocity field may seem like a trivial problem, and it is somewhat hard to believe that it's actually a very difficult one that many people have worked on. The obvious question is, of course, why is advecting a blob with a given velocity hard? Can't we simply take a standard method suitable for the solution of a hyperbolic equation and use that? In the figure, we show the results of doing exactly that for a one-dimensional advection with u equal to 1. We use two standard numerical methods, the first-order upwind method and the second-order Lax-Wendorf method. The initial conditions consist of a steep change at the left boundary, and the figure shows the results after the marker function has been advected 0.6 times the domain length to the right, using 80 grid points to resolve the whole domain. The thin black line shows what the solution should look like, and it's obvious that neither method does a good job. The blue line shows that the first-order method smears out the steep change in h, and the high-order method, the red line, produces a solution with large oscillations behind the step. This is what is generally found for linear or classical schemes. First-order methods result in excessive smearing, and higher-order methods introduce oscillations. While nonlinear schemes have been developed that do a much better job at capturing a sharp discontinuity without oscillations, they tend to do very well for shocks in compressible flows and not quite as well for interfaces separating different fluids. Furthermore, since the value on both sides of the discontinuity are known, one is 0 and the other one is 1, it seems that we should be able to come up with methods that do better. This is indeed the case, and several methods have been designed for the specific task of advecting a marker function that takes one constant value on one side of the interface and another constant value on the other. Of the several methods that have been designed to advect a marker function that takes one constant value on one side of the interface and another constant value on the other, the best known are the volume of fluid method, where the average value of the marker function in each cell is updated by computing the flux of markers between cells, the level set method, where the interface is identified as zero contour of a smooth function advected by methods for hyperbolic functions with smooth solutions, and the front tracking method, where the interface is marked by connected marker points that are moved by the fluid velocity interpolated from a fixed grid. All of those methods come in several different versions. Notice that only in the volume of fluid method is the marker function updated directly, and in both the level set and the front tracking method, we need to construct the marker function from the interface location. Although the method listed on the previous slide have much in common, they differ in exactly what is advected and how the marker function is approximated. In the volume of fluid method, we work with the average value of the marker in each computational cell and advect the marker directly. In the figure, this is shown by C, which has a constant value everywhere, either 0 or 1, except in the interface cell J. In the level set method, we advect a smooth function, phi of x, shown by a nearly straight dashed dot line in the figure, which crosses the 0 axis where the interface is located. And in front tracking method, we advect a point that is located exactly where the interface is, or where the discontinuity in h is. We do, however, need a marker function, so for both level set and front tracking methods, this needs to be constructed from the interface location. Although the construction of the marker function is different, in both methods the marker is generally taken to have a smooth transition from one constant value to the next, so that it looks like the dashed line shown by I of x in the figure. We now take a slightly closer look at these methods. The volume of fluid method is the most widely used approach to update the marker function. In one dimension, the advection of a sharp discontinuity separating regions of constant value is exact. This makes it a natural starting point for multidimensional problems, but unfortunately the extension to higher dimension is far from trivial and requires making rather significant approximations. The challenge of advecting a marker function using a standard finite volume method is best introduced by an example. Consider the situation in the figure. The interface is located in the middle cell, and since we only keep the average value of the marker function, the cell is half full. By itself, the average values does not specify the exact location of the interface, since in general there are two possibilities, depending on whether fluid 1 is located to the left or right of the interface. To update the marker, we compute the flux of the marker through the boundary, and for the linear advection equation this is easily done. Indeed, given the initial condition, we simply move the marker with a constant velocity to the left or right, depending on the sign of the velocity. If the velocity is positive, the marker moves to the right, and we update the marker by moving everything at distance u delta t to the right, as shown in the middle frame, and then average, as shown in the frame on the right. Unfortunately, the interface is now spread over two shells, and if we continue the process, the interface will continue to spread out or diffuse over more and more shells. The problem, obviously, is that we took the initial conditions to be the average value in the cell, so when we move the marker to the right, the cell on the right of the interface cells starts to receive marker, even if the middle cell is not full. The solution is to look to the neighboring cells, determine that the marker is non-zero on the left, in this case, and use that to reconstruct more realistic initial conditions. It is, in particular, easy to determine exactly where the interface is. If the value is Cj, then the interface is Cj times delta x from the left boundary, and if the size of the time step is such that the interface moves less than 1 minus Cj times delta x, or when u delta t is less than 1 minus Cj delta x, then nothing should flow into the cell on the right. If the time is greater, or if u delta t is greater than 1 minus Cj times delta x, then the total amount of C that flows from cell j to cell j plus 1 is u delta t minus the amount of C that remained in cell j, or delta x minus Cj times u delta t. The flux through the right boundary of the middle cell is therefore 0 if the delta t is less than 1 minus Cj times delta x divided by u, and delta x minus Cj plus u times delta t if delta t is greater than 1 minus Cj times delta x divided by u. The flux into the cell is simply u times delta t, since C in the j minus 1 cell is equal to 1. The key here is that we located the interface exactly by examining the neighboring cells, and this allowed us to write down the exact flux in such a way that the cell fills up one by one and no diffusion takes place. The simplest extension of this straightforward method to 2 and 3 dimension is to do the advection in one direction at a time using the one-dimensional formulation. In this approach, known as the simple line interface calculation, or SLIC, we construct a horizontal interface for advection in the vertical direction, followed by constructing a vertical interface for advection in the horizontal direction. The problem with this approach is that the cells on either side of the interface are not always full or completely empty, and not only does that introduce uncertainty in locating the interface, but the interface can also break up due to the generation of partially full cells away from the interface. In an effort to improve the SLIC method, Hurt and Nicholas suggested that the interface in each cell should be approximated as either a vertical or horizontal one, based on a normal vector estimated by considering the volume fraction in neighboring cells. While this did not result in a significant improvement, it suggested that an interface reconstruction based on the normal might lead to better results. This is indeed the case, and the next improvement was the piecewise linear calculation method, or PLIC, where the interface is assumed to consist of a line whose orientation is based on an estimation of the normal to the interface, and whose location is adjusted such that the average value of the marker in the interface cell is correct. This improved considerably the performance of the volume of fluid methods, but at the cost of much more complex flux calculation. This slide shows the various versions of the volume of fluid method schematically. The configuration of the fluid interface and the grid used to represent the field is shown in the upper left corner. The original split WOF method, the slick method, is shown in the upper right corner, where the solid and the dashed line show the orientation for advection in a different direction. The Hurt and Nichols method, where the interface in each cell is assumed to be either vertical or horizontal, is shown in the lower left corner. And finally, the Plick method, where the interface is approximated by a sloping line that may be discontinuous as cell boundaries, is shown in the lower right corner. More sophisticated WOF methods are continuously being developed, and many of those do an excellent job of following sharp interfaces. There are many versions of Plick, but in all cases the first step is to estimate the normal vector in each cell, given the marker function in the cell that we are considering and in the neighboring cells. Once we have the normal, we draw a line perpendicular to the normal and move it in the direction of the normal until the area cut out from the interface cell by the line matches the value of the marker function in the cell. Knowing the shape of the region occupied by the marker function in each interface cell then allows us to advect the marker using geometric considerations. The normal can be found in many ways, but in most cases it is estimated to be the gradient of the marker function. Since the marker function changes abruptly from 1 to 0 over only one cell, some smoothing is generally involved, but the simplest approximation is to use center differences as shown here. Notice that both the interface cells and the cell close to the interface have a non-zero normal. Once the normal is found, the slope of the interface is known. We approximate the interface by a straight line perpendicular to the normal, and the location of the interface is found by moving it along the normal until the area below the interface matches the volume fraction of the marker in the interface cell. The marker can be advected in several ways, but the simplest approach is to advect it first in one direction and then in the other. Consider the cell shown in the figure, where the interface cuts through the top and the right side of the cell, and the cells to the left and below are full. If we assume that the velocity remains constant during the time step, then advection in the x direction corresponds to shifting everything in a cell at distance equal to u times delta t, where u is the x component of the velocity. Here, the gray region on the right will move out of cell I, j, and the gray region on the left will move into cell I, j. Thus, the total amount of marker that flows into cell I, j from the cell on the left, I minus 1, j, is given by the gray tall rectangle on the left, and the total amount of marker that flows out of cell I, j into cell I plus 1, j on the right is given by the gray polygon on the right. The advection in the y direction is done in the same way. The interface is reconstructed from the fraction of the marker in the interface cell and the normal vector computed using the amount of marker in the neighboring cells, and the regions that will move into new cells are identified. Here, the gray region at the top will move out of cell I, j, and the gray region at the bottom will move into cell I, j. The total amount of marker that flows into cell I, j from the cell on the bottom, I, j minus 1, is given by the gray white rectangle at the bottom, and the total amount of marker that flows out of cell I, j into cell I, j plus 1 is given by the gray polygon on the top. To maintain symmetry with respect to x and y, the order of advection is usually alternated. The approach described here conserves the marker function c, since what flows out of one cell flows into another cell, but does not guarantee that it remains bounded between 0 and 1. However, more advanced method exists that both conserve c and ensure that it is bounded between 0 and 1. For fully three-dimensional schemes, both the reconstruction of the interface as well as the advection are considerably more complex and require careful consideration of the interface geometry. Given how difficult it is to advect a sharp interface in multidimension, we might ask why bother with a sharp interface at all. The interface can be identified as a constant value contour of a smooth function, and it's much easier to advect smooth fields than discontinuous one. This is the idea behind the level set method. In the level set method, we identify the interface with a given value, usually taken to be 0, of a smooth function phi. Phi is then advected with the fluid, and since the interface is a material point, the 0 contour, or the level set, is advected as well. Since it's only the normal velocity that matters, the advection equation is usually rewritten by using that the unit normal to the interface can be found as the gradient of the level set function divided by the magnitude of the gradient, and that the velocity dotted into the unit normal is the normal velocity. Wherever the level set function phi is 0, there is an interface, and for the two peaked functions shown here, there are two closed interfaces since two peaks stick out through the 0 plane. While the interface is generally accurately advected using a level set method, what we need is to update the marker function. The 0 level set only gives us the location of the interface. Thus, we need to map the smooth level set function into a marker function that changes rapidly but smoothly from one constant value to another value. Furthermore, we generally want the shape of the transition shown to remain more or less the same everywhere and at all times. If the shape of the level set function in the vicinity of the 0 contour remained the same, this would be easily accomplished, and we would simply pick a mapping function, such as the sine function shown here. Once the marker function has been determined, we can obviously also find a smooth approximation to the delta function by differentiation. This can obviously be related to the level set function as shown at the bottom of the slide. Unfortunately, the level set function is generally distorted significantly by non-uniform flows around the interface. If the interface is being stretched, for example, the gradient of the level set function increases, and if it is compressed, the gradient decreases, making the level set function flatter. In the example here, where we have stagnation point flow on the left, the level set function is compressed, making the transition in the marker function steeper, and on the right, where the flow is reversed, the transition shown becomes thicker. In order to make the marker function transition from one value to the other in the same way everywhere, the level set function must be reset in such a way that its slope is always the same next to the interface. In the original level set method, this was achieved by reinitializing the level set function so that it remained a distance function whose value was equal to the shortest distance to the interface. The gradient of a distance function is normal to the interface and should remain unity for the level set function to remain a distance function. This can be done by setting the difference between the absolute value of the gradient and unity equal to the time derivative of the level set function and solving it in a pseudo time where the interface remains stationary and the real time is frozen. Obviously, if the time derivative is 0, then the absolute value of the gradient is equal to unity. The sine function accounts for the fact that the level set function changes sign across the interface, but the gradient does not. Usually, we are only concerned with the shape of the level set function close to the interface, and we only need to solve the reinitialization equation to correct the shape there. Unlike the VOF method, where the marker function is updated directly, in the level set method, the update of the marker function is a two-step process. First, the interface is advected, and second, the marker function is constructed from the smooth function. Front tracking is also a two-step process where the interface is first moved and the marker function is then constructed. The identification of the interface and how it is moved is, however, very different. In its simplest embodiment, the interface in front tracking is represented by connected marker particles that move with the fluid velocity. For two-dimensional flows, the front is simply a string of points, but in three-dimension, the front is a two-dimensional surface that needs to be represented by a surface grid of some sort to account for the connectivity of the markers. The marker particles and the connections are usually referred to as the front. The marker particles are advected by the fluid velocity, interpolated from the grid used to solve the Navier-Stokes equations. The marker function is then constructed from the location of the front and used to set the density and the viscosity. The front is also used to compute the surface tension, which must be distributed to the fixed grid and added to the Navier-Stokes equations. The front usually deforms as the flow evolves and must be modified by adding and deleting marker points. Here we show the front and the fixed grid used to solve the Navier-Stokes equations. Fluid solver is usually a relatively standard finite volume method implemented on a regular structured grid, although as with the level set and the volume of fluid method, we can in principle use any flow solver. For three-dimensional flow, the interface is an embedded two-dimensional surface, and since its geometry can be fairly complex, we usually use an unstructured grid typically consisting of points that are connected by triangular elements. Generally, the size of the triangular elements is some fraction of the size of the control volumes used for the fluid flow, and as the flow evolves, the unstructured two-dimensional grid is deformed, stretched, and compressed. Thus, it is usually necessary to update the grid once in a while to maintain the resolution. This updating, where we need to add and delete points and elements and sometimes change the topology, is generally considered the main challenge with front tracking. In the next lecture, we will focus on two-dimensional flow, where the front is simply a one-dimensional curve and adding and deleting points is relatively simple. Implementation of front tracking methods requires several steps. We usually move the front with the fluid velocities, which must be interpolated from the fixed grid used to solve the Navier-Stokes equations. Then we need to construct the marker function from the location of the front, and for immiscible fluids we need to find the surface tension from the front geometry and add it to the discrete Navier-Stokes equations on the fixed grid. We can do these operations in several different ways, and in the next lectures we will work through one relatively simple approach. Although our implementation focuses on two-dimensional flows, which are considerably simpler than fully three-dimensional ones, the underlying ideas remain the same. Several other methods have been developed to capture sharp interfaces, including hybrid methods such as the particle level set and combined volume of fluid level set methods, as well as methods that capture the interface more sharply, such as the ghost fluid method and the immersed interface method. Considerable effort has also been devoted to the development of similar approaches to capture rigid and elastic boundaries, both moving and stationary. Of the elementary methods described in this lecture, front tracking appears to be the most robust and accurate approach, and while work on both level set and volume of fluid method continues, the front tracking approach described here is still often used in more or less its original form. In the next lecture, we will describe a simple implementation in sufficient detail so that we can code it up.